To really understand what's going on in this circuit, Renee and I built this Falstad simulation, and this is actually what we use to base our PCB off of. And analyzing it one step at a time really makes things make a lot of sense. So if we start here with the instrumentation current sensor, and let's just actually forget about the instrumentation amplifier for right now, and just focus on this part of the circuit. So you see this 5.6 ohm here. This is actually going to be our load resistor. This could be anything from a DC brushless motor to a computer fan to a light bulb. The resistance really doesn't matter. It's just there to be our load. But this right here is our shunt resistor, or our current sensing resistor, and its resistance really does matter. We need to make sure that we keep this exactly how it is, because the basis of our current detection is actually using Ohm's law. So if we know we have an 100 milliohm resistor here, and we know the voltage across it via the instrumentation amplifier, then we actually know the current going through it. And if we put it in series with our load, we know the current going through our load as well. And these low pass filters here are really just to give us straight DC and kind of forget about the PWM going on here. So if our instrumentation current sensor has a gain of 100 and our shunt resistor is 0.1 ohms, 0.1 times 100 is 10. Now if you look at the average milliamps here going through our load, it's just right around 208 milliamps. And if we look at the output voltage of our current sensor, we can see that it's 2.08 volts, which is exactly 10 times the current going through this. So essentially what we're doing is we are taking the current going through our load, multiplying it by 10, and now we have an analog voltage for the rest of our circuit to work with that corresponds directly with the current going through the load. So you might be wondering how we take a current sensor like this and turn it into a constant current device, meaning we can change the supply voltage or the load resistance and still get a constant current, assuming our supply voltage is capable of supplying the current demanded. Well, we're going to need an error amplifier. We're going to need something to tell us that, hey, the current you have right now is not right. And you can see here on one of the inputs, we're just going to have a potentiometer, which is essentially our reference voltage that we are setting for this. And what it's saying is, hey, I want the current to be this value. And that's going to be compared to what the current actually is, which is the output from this amplifier right up here. This error amplifier is always going to try to have 0 volt difference because we want 0 error, right? So you can see right now 2.09 and 2.07, there's almost 0 volts difference between the two, which means we are currently sitting at a good spot. And that's all due to the PID controller, which I'll go over next. But what's going to happen if I make a sudden change in the supply voltage? We can see how the error amplifier reacts. So if I increase the supply voltage, you can see here, all right, now there's a lot of error. The current that we are demanding is not anything close to what the current actually is. So what's going to happen is our PID controller is going to try to correct this and give us 0 volts again on the output of the error amplifier. And that's what you're seeing here. So it might take a second, it might oscillate around 0, but eventually it's going to stabilize to 0 volts over here. All right, so now the question is, what is the PID controller and how does it help us achieve 0 error on the error amplifier? Well, we're actually going to take our output, V error, and we're going to input it into these 3 stages: the proportional stage, the integral stage, and the derivative stage. And these are each going to contribute their own separate response to the summing stage, where we essentially sum it all up and give our total output called I set. And we can change how much each one's contributing if we just change the value of these resistors here. So for the sake of demonstration, I'm going to go over each individual amplifier here, and I'm going to show on the screen what happens if we change the supply voltage suddenly, so you can see how the amplifier actually responds. So the first one is the proportional stage, and this is actually just a normal inverting amplifier. So what you're going to see is the proportional stage is going to provide an immediate proportional response to the error. So a large error is going to be a large output, and a small error is going to be a small output. It's essentially the immediate correction signal. The next one is the integral stage, which is just an integrator op-amp. This one is actually arguably going to be the most important because it's going to accumulate the error signal over time. So if there's any persistent steady state error, for example, if our current is actually 1% lower than what we want it to be, then the integrator is going to pick up on this and slowly increase its output until the error is forced to exactly 0. And it's really helpful for us because it's going to hold on to this analog voltage that's later going to be used for the PWM generator. And this analog voltage is really important for getting the exact duty cycle that we need. So unlike the other amplifiers, when they have 0 error, they're going to have 0 output. But in this case, when we have 0 error, we're actually going to contribute nothing to the integral. So it's just going to hold on to this voltage here. And then lastly, we have the derivative stage, which is essentially an op-amp and a differentiator configuration. So what it's going to do is, if we provide a sudden change in the supply voltage, like so, it's going to look at the rate of the change of the error, and if the current is changing very rapidly, it's going to provide a counteracting signal to dampen the response. It prevents overshoots and oscillations, and it's going to help stabilize the system. So I really didn't talk about the values that each one of these stages have in the PID controller, and that's because it's really subjective to your personal application. On an analyzed PCB, you have potentiometers for each one of these stages, so they can influence the output really depending on how much we need. And you can see a PID controller can actually provide a critically damped, underdamped, or overdamped response, very similar to an RLC circuit. And earlier I was demonstrating the underdamped case because I kind of feel like you can visually see the PID controller correcting better than any of the other cases. But if we were to tune the values a little better, then we can get it critically damped and the response would be almost immediate. So once we're done with all the stages of the PID controller, we get the analog voltage on the output of the summing stage. And in this case, it looks like it's 200 millivolts. So this 200 millivolts is going to be compared to a triangle wave. You may remember from Wallace's class that Class D amplifiers actually compare an analog voltage to a triangle wave to generate PWM. And that's exactly what we're doing here. And this PWM is used to drive the low side MOSFET on our load. So that effectively is what's actually varying the current to our load. So now you can kind of see how the feedback system works as a whole. An element of the circuit is changed, like a change in the load resistance or the supply voltage. Errors seen on the error amplifier, and the PID controller will respond to the error and adjust the duty cycle driving the load until the integrator finally finds the correct analog voltage to keep the error at 0. This creates our constant current. So this is the quick demonstration of the system in action. You can see I have 207.5 milliamps at the start. I'm going to change the load from 8 to 4 ohms, and you can see the total system response here. I have the entire outputs of the PID controller, as well as the error amplifier and the current through the shunt resistor. You can see that if I divide the load in half from 8 to 4, it's just going to decrease the duty cycle, and we're going to get right around the same current with an error of 1.2% after the system does its total response. And here I'm just showing that if we start at 208 milliamps and we want to change the value of the current through the load, we can just change the error reference voltage and the current's going to change.